Okay, we're going to look at direct variation, slope, and tangent. Okay, so if we had a roof, for example, okay, and we have all these supports, okay, they're 1.5 feet high, 3 feet high, 4.5 feet high, 6 feet high, 7.5 feet high. And in between each of those verticals is 2 feet. If we were to complete this table, okay, so the distance between post 1 and post 2 is going to be 2, okay, and then it's going to be 4. So the horizontal distance of post from eaves, okay, so it's 2 away, it's 4 away, it's 6 away, right, it's 8 away, and it's 10 away. Okay, and then my vertical from there, so it's over 2, and then your vertical is 1.5. If we're over 4, my vertical is 3. If we're over 6, my vertical is 4.5, okay? So if I did h over d, so in other words, if I take 1.5 divided by 2, I get 0.75. If I take 3 divided by 4, I get 0.75. If I take 4.5 divided by 6, I get 0.75. See the pattern? 6 divided by 8, and 7.5 divided by 10. So no matter what, my ratio is the same. So my height to my distance is always 0.75. Okay, so direct variation is when two variable quantities have a constant ratio. The variation constant is the constant ratio formed from a direct variation relationship, which looks like this. Okay, so for our h over d situation, the h over d is your ratio of quantities. And when I divide those two and get a number, that's my variation constant. Okay, so the variation constant in this, okay, of course, would be 80. We're just looking for the number. The variation constant in this one would be 0.2. Okay, a direct variation equation can be used to determine a missing value. Example, if h over d is 0.75 and we know h is 4, we can find d. So first we're going to rewrite it so it no longer has a fraction in it. So we had h over d equals 0.75. If I multiply both sides by d, that's going to get rid of that fraction. Whatever I do to one side, I do to the other. So if I rewrite it, it's h equals 0.75 d. Now substitute and solve. Okay, so if h is 4, the rest of it's the same, right? Okay, so then let's see, if I want to figure out what d is, I would have to divide both sides by 0.75. 0.75. This is going to cancel, this is going to cancel, and that's going to get me my answer of 5.3 repeating, or 5 1/3. Okay? Alright, slope of a line. Measure of the steepness of a line, the ratio of rise to run for any 2 points on the line. Okay, this is a video from Khan Academy that I'd like you to watch. If it will play, there we go.
Find the slope of the line in the graph. And just as a bit of a review, slope is just telling us how steep a line is. And the best way to view it, slope is equal to change in y.
Let's put this on full screen.
In y over change in x. Over change in x. And for a constant, this will for a line, this will always be constant. And sometimes you might see it written like this. You might see this triangle, that's a capital delta, that means change in y over change in x. That's just a fancy way of saying change in y over change in x. So let's see what this change in y is for any change in x. So let's start at some point that seems pretty reasonable to read from this table right here, from this graph. So let's see, we're starting here, then let me do it in a more vibrant color. So let's say we start at that point right there, and we want to go to another point that's pretty straightforward to read, so we can move to that point right there. We can literally pick any 2 points on this line. I'm just picking ones that are at nice integer coordinates, so it's easy to read. So what is the change in y and what is the change in x? So first let's look at the change in x. So if we go from there to there, if we go from there to there, what is the change in x? My change in x is equal to what? Well, I could just count it out. I went 1 step, 2 steps, 3 steps. My change in x is 3. And you can even see it from the x values. If I go from -3 to 0, I went up by 3. So my change in x is 3. So let me write this. Change in x, delta x is equal to 3. And what's my change in y? Well, my change in y, I'm going from -3 up to -1. Or you could just say, 1, 2. So my change in y is equal to positive 2. So let me write that down. Change in y is equal to 2. So what is my change in y for a change in x? Well, when my change in x was 3, my change in y is 2. So this is my slope. And one thing I want to do, I want to show you that I could have really picked any 2 points here. Let's say I didn't pick, let me clear this out. Let's say I didn't pick those 2 points. Let me pick some other points, and I'll even go in a different direction. And I want to show you that you're going to get the same answer. Let's say I view this as my starting point, and I want to go all the way over there. So what is my, well, let's think about the change in y first. So the change in y, I am going down by how many? How many units? 1, 2, 3, 4 units. So my change in y in this example is -4. I went from 1 to -3. That's -4. That's my change in y. Change in y is equal to -4. Now what is my change in x? Well, I'm going from this point, or from this x value, all the way, let me do that in a different color, all the way back like this. So I'm going to the left, so it's going to be a negative change in x. And I went 1, 2, 3, 4, 5, 6 units back. So my change in x is equal to -6. Change in x is equal to -6. And you can even see I started at an x is equal to 3, and I went all the way to x is equal to a -3. That's a change of -6. I went 6 to the left, or a change of -6. So what is my change in y over change in x? My change in y over change in x is equal to -4 over -6. The negatives cancel out, and what's 4 over 6? Well, that's just 2 over 3. So it's the same value, you just have to be consistent. If this is my start point, I went down 4, and then I went back 6. -4 over -6. If I view this as my starting point, I could say that I went up 4, so it'd be a change in y would be 4, and then my change in x would be 6. And either way, once again, change in y over change in x is going to be 4 over 6, 2/3. So no matter which point you choose, as long as you kind of think about it in a consistent way, you're going to get the same value for slope.
Okay, so let's go back to here. All right, so let's use that information and let's figure out what we have for the slope. Okay, so like he said, you're going to look for a spot. I don't want this point because it's not a good spot, but if I go here and here, okay, so my rise is up 100, 200, 300, 400, 500. Okay, and my run is 10, 20, 30, 40, 50, 60. Well, I can cancel that, right, to 50 over 6. Let's see, those are both divisible by 2. So we'd have 25/3. Sorry if you can't see that. 25/3 would be my slope. Okay, this one, well, we can count from any of them. Looks like they all are at good spots. So I'll count from any of the points, from one point to another. So this side would be a rise of 2 and a run of 2. Well, 2 over 2 is just 1, so my slope would be 1 in this case. Okay, here's a good spot. Here's a good spot. So I'm going a rise of 2, 4, 6. And my run is by 1, so 1, 2. So here my slope would be 3. So they're not being consistent with their counting, so just keep that in mind. Okay, watch to see what everybody's counting by in your graphs. All right, here's one here, here. So my rise is 5, 10, 15, 20. And my run is 2, 4, 6, 8, 10. Of course would be 2. Okay, let's see, that didn't copy very well, but we could count from here to here. I'm going down 1, 2, 3, 4, 5, 6. And then I'm going over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So negative 6/10, which would reduce to negative 3/5. This one's a little more consistent because I did both of them as by ones. Okay, tangent. We talked about this a little bit the other day when we had the sine and the cosine. The third ratio is tangent. It's the ratio of the acute angle compares the two legs. Okay, so this one doesn't have anything to do with the hypotenuse. It's the ratio of the opposite leg to the adjacent leg. So if I'm looking from A, tangent would be this over this. Okay, nothing to do with the hypotenuse on tangent. Okay, and then I mentioned this briefly the other day, the SOHCAHTOA. Sine is opposite leg over hypotenuse. Cosine is adjacent leg over hypotenuse. Tangent is going to be opposite leg over adjacent leg. Okay, so to put that into practice, if we did sine of C, sine would be opposite, which is 4, over hypotenuse, which is 5. If I did cosine of C, that would be, adjacent, which is 3, over hypotenuse, which is 5. Tangent of C would be opposite, which is 4, over adjacent, which is 3. Okay? And if I had tan of B, opposite would be up here, and then adjacent right there. Okay, so tangent of A on this particular situation, this is going back to the beginning where we had the beam and we had the post and the roof, okay? So tangent of A, so from here, tangent would be opposite, which is 7.5, over adjacent, which is 10. Well, that simplifies to 0.75. If I did slope of AB, okay, that means rise over run. Well, my rise is 7.5. My run is 10. So 0.75. And direct variation is height over distance. Well, my height is from here to here, 7.5. My horizontal distance from here to here is 10. So 0.75. So the reason they put all three of these together is because they all have the relationship, okay, where we had the opposite over adjacent, rise over run, and height over distance for our ratio. Okay, it could be put into play, for example, in our school. Okay, you get rise over run. We can figure out what the slope of the roof is. Okay.